Hey, welcome back. In this video, we're going to continue discussing linear recurrence equations. We're going to focus especially on the Fibonacci numbers. And we're going to see how to solve linear recurrence equations in general. Let's start by defining the Fibonacci numbers. We define them by letting f of 1 equal f of 2 equal 1, and f of n plus 2 equals f of n plus 1 plus f of n for all n greater than or equal to 0. And we call f of n the nth Fibonacci number. Fibonacci numbers have a lot of applications, including in computer science and in biology. They show up in particular a lot in nature. For example, if you look at petal counts and the counts for spirals in flowers, these will often end up being Fibonacci numbers. More specifically, if you look at the number of spirals of different colors in yellow chamomile flowers, or you look at the patterns of florets on sunflowers, or if you look at pine cones, pineapples, or the family trees of honeybees, you will find Fibonacci numbers. Let's look a little more at the bees. So why do we get Fibonacci numbers when we look at the family trees of honeybees? Well, it's because female bees, like humans, typically have two parents, a female and a male. Male bees have one parent, a female. This means that female bees have three grandparents. Their mothers have two parents, and their fathers have one parent. So 2 plus 1 gives us 3. The male bees, however, only have two grandparents because their only grandparents are from their mom, and their mom has two parents. We can look at the great-grandparents for the female bees. We see that there are 5 of them. We get to 5 by adding together the number of grandparents for their mother and the number of grandparents for their father. Their mother has 3 grandparents, their father has 2 grandparents. 3 plus 2 gives us 5. And if we look at the number of great-grandparents for the male bees, well, the number of great-grandparents for the male bees is the same as the number of grandparents for their moms, and that's just 3. We can continue this way, and we see that the female bees have 8 great-great-grandparents, and the male bees have 5 great-great-grandparents. More generally, we can see that the female bees have f of n plus 4 great to the n grandparents, where f of n plus 4 is the n plus 4th Fibonacci number. How do we get that? Well, f of n plus 4 is equal to f of n plus 2 plus f of n plus 3, where f of n plus 2 is the number of great to the n minus 1 grandparents of their father, and f of n plus 3 is the number of great to the n minus 1 grandparents of their mother. The male bees, on the other hand, have f of n plus 3 great to the n grandparents. This number is the same as the number of great to the n minus 1 grandparents of their mothers. So that's why we see Fibonacci numbers in the family trees of the bees. It's because the male bees only have a mother, they don't have a father. So for the rest of the video, I'd like to look at some interesting properties of the Fibonacci numbers, and then we'll look at how to solve linear recurrence equations in general, and we'll solve to find an explicit formula for the Fibonacci numbers that doesn't use any recursion or any summations. So the first property that I claim is true is that this summation, the sum from I equals 1 to n of f of I, the I Fibonacci number, that sum is equal to f of n plus 2 minus 1. In other words, 1 less than the n plus second Fibonacci number. I claim this holds for all n greater than or equal to 1. We can prove this using induction. In fact, we can prove it using weak induction. We don't even need to use strong induction. Since we're using weak induction, we'll just have a single base case. The base case will be n equals 1. At n equals 1, the sum is just a sum from I equals 1 to 1, so it only has one term. And that term is just f of 1. F of 1 equals 1, and 1 is the same as 2 minus 1, and 2 minus 1 is the same as f of 3 minus 1, which is f of 1 plus 2 minus 1. So that's how we get the base case. For the inductive step, we have an inductive hypothesis. We assume that the sum from I equals 1 to k of f of I is equal to f of k plus 2 minus 1. And our goal with this inductive step is to show that the sum from I equals 1 to k plus 1 of f of I is equal to f of k plus 3 minus 1. And we can see that this is true, since we can start with that sum on the left, the sum from I equals 1 to k plus 1 of f of I. We can pull out the f of k plus 1 term, and we can write it as f of k plus 1 plus the sum from I equals 1 to k of f of I. And then here we can just use our inductive hypothesis to substitute f of k plus 2 minus 1 for the sum. And that gives us f of k plus 1 plus f of k plus 2 minus 1. And we can use the definition of the Fibonacci numbers, their recurrence equation, to substitute an f of k plus 3 for the f of k plus 1 plus f of k plus 2. And that leaves us with f of k plus 3 minus 1, which is exactly what we were trying to get. Here's another property of the Fibonacci numbers, and I'm going to leave it to you to prove this. Prove that the sum from I equals 0 to n of f of 2i plus 1 is equal to f of 2n plus 2 for each n greater than or equal to 0. So for some small values of n, the sum from I equals 0 to 0 of f of 2i plus 1. This is just f of 1. The sum I equals 0 to 1 of f of 2i plus 1. This is f of 1 plus f of 3. And if we look at n equals 2, we get the sum I equals 0 to 2 of f of 2i plus 1. And that equals f of 1 plus f of 3 plus f of 5. We can write a few Fibonacci numbers up here. So we have 1 and 2, they're both 1. F of 3 is 2. F of 4 is 1 plus 2 is 3. We got a 5 for f of 5. And f of 6 is 8. So we can see f of 1, this one equals f of 2. And 2 there is 2n plus 2 when n is 0. F of 1 plus f of 3, that gives us f of 4. Again, that's a 2n plus 2 for n equals 1 this time. N equals 0 equals 2 down here. And if we add f of 1 plus f of 3 plus f of 5, we see that we get 1 plus 2 plus 5 is 8, and that's f of 6. And again, that's the 2n plus 2, that's 6. when n equals 2. So the goal with this problem is to show that that pattern continues. So prove that that summation always gives you f of 2n plus 2. You might want to use induction to prove that, but any method that you can get to work to prove that is perfectly fine. Let's look at another interesting property of the Fibonacci numbers. We can see that for all n greater than or equal to 0, both f of 3n plus 1 and f of 3n plus 2 are odd, but f of 3n plus 3 is even. Let's see why that's true. This is another one that we can prove by induction, and we only need weak induction to prove this. For the base case, we'll do that as n equals 0. And for n equals 0, we have to check 3 elements of the Fibonacci sequence. We have to check f of 1, which is 1, and we note that that's odd. F of 2 is also 1, it's also odd. And f of 3 is 2, and that's even. So we see that when n equals 0, the statement is true, that f of 3n plus 1 and f of 3n plus 2 are odd, and f of 3n plus 3 is even. For our inductive step, we'll have an inductive hypothesis where we assume that both f of 3k plus 1 and f of 3k plus 2 are odd, and f of 3k plus 3 is even. Our goal will be to show that f of 3k plus 4 and f of 3k plus 5 are odd, and f of 3k plus 6 is even. In order to show that, we can use our recurrence equation for the Fibonacci sequence. That gives us that f of 3k plus 4 equals f of 3k plus 3 plus f of 3k plus 2. F of 3k plus 3 is even, f of 3k plus 2 is odd, so we get an even plus an odd, which gives us an odd. For f of 3k plus 5, the recurrence equation gives us f of 3k plus 4 plus f of 3k plus 3. F of 3k plus 4 we just saw was odd. F of 3k plus 3 is even, so we get an odd plus an even. This gives us an odd. Finally, we can check f of 3k plus 6. Using the recurrence equation, we get f of 3k plus 6 equals f of 3k plus 5 plus f of 3k plus 4. F of 3k plus 5 we just saw was odd. F of 3k plus 4 we also saw was odd. So when we add an odd and an odd, that gives us an even for f of 3k plus 6. And that concludes the induction. Here's one last property that we can look at with Fibonacci numbers. So this property uses matrices. We have this matrix Q here. Q equals 1, 1, 1, 0. It's a 2 by 2 matrix. And we look at powers of Q. So the first power we look at is Q squared. When we want to multiply Q squared, we just multiply Q times itself. So we have 1, 1, 1, 0, 1, 1, 1, 0. And how do we get each element of the product? Let's look at that for a second. So this first element right here, I'll put it in a box since we didn't get it yet. We get that by taking the dot product of the first column of the right matrix with the first row of the left matrix. When we take that dot product, we get this one right here times this one right here plus this one right here times this one right here. That gives us a 2 right here. For the entry right here, so this one and that one together gave us that. This one down here, we use this same column right here, the first column of the right matrix, but we dot it instead with the second row of the left matrix. So the 1 times the 1 here plus this one times this 0. That gives us a 1. And that was from this and this. Now this entry right here, we get that by taking the dot product of the second column of the right matrix with the first row of the left matrix. So we get a 1 times a 1 plus a 0 times a 1, which gives us a 1 again. And finally, this last entry right here, we get that by taking the dot product of the second column of the right matrix and the second row of the left matrix. So we get a 1 times a 1 plus a 0 times a 0. That gives us a 1. So we got 2, 1, 1, 1. So that's q squared. And we can keep on calculating powers of q like this. So we can look at what is q cubed. To get q cubed, we can take q squared times q. So we can do 2, 1, 1, 1 times 1, 1, 1, 0. For the top left, we take the dot product of the first row of the left matrix and the first column of the right matrix. This gives us 2 times 1 plus 1 times 1. We got a 3 right there. For the top right entry, we take the dot product of the first row of the left matrix and the second column of the right matrix. So we get a 2 times 1 plus a 1 times 0. We got a 2. The bottom left, to get that, we take the dot product of the second row of the left matrix and the first column of the right matrix. So we get a 1 times 1 plus a 1 times 1. And that gives us a 2. And finally, the last entry of this matrix is the dot product of the second row of the left matrix and the second column of the right matrix. So we get a 1 times 1 plus a 1 times 0. This just gives us 3, 2, 2, 1. And we can continue. We can get q to the 4th and q to the 5th. I won't multiply those out. For q to the 4th, we get 5, 3, 3, 2. And for q to the 5th, we get 8, 5, 5, 3. And it's interesting because these entries in these powers of q, we're seeing Fibonacci numbers in the entries. So we're seeing 1, 2, 3, 5, 8. We would maybe expect to see a 13 in q to the 6th. So the problem for you to think about is to find and to prove a simplest formula for the entries of q to the n in terms of the Fibonacci numbers. So for the remainder of this video, we're going to focus on solving linear recurrence equations. Before we talk about how to solve them, let's quickly review what a linear recurrence equation is. So we'll start with the definition of a recurrence equation. This is just an equation that defines a sequence recursively. A linear recurrence equation is just a recurrence equation for some sequence. We call the sequence A1, A2, A3, and so on. You can use any letter you want. It's not important that we use A's. And the linear recurrence equation defines A sub n as a linear polynomial of A sub n minus 1, A sub n minus 2, A sub n minus 3, and so on. In other words, it defines A sub n as a polynomial of degree 1 in the previous terms of the sequence. Here's an example of a typical linear recurrence equation. A sub n equals A sub n minus 1 plus A sub n minus 2. We've seen that linear recurrence equation many times, including in this video, because that's the linear recurrence equation for the Fibonacci sequence. The thing is, there's many sequences that have that linear recurrence equation, because the fact that we get the Fibonacci sequence depends on the initial values, specifically the values for A1 and A2, or any two distinct values in our sequence. So now that we reviewed linear recurrence equations and what they are, we're going to see a general method for solving to get an explicit formula for a given linear recurrence equation. The explicit formulas that we find will not use any recursion or summations. They'll just use exponentiation and linear combinations. So suppose that we have some general linear recurrence equation. A general linear recurrence equation we can write in the form a sub n equals the sum from I equals 1 to k of c sub I times a sub n minus I, where c sub 1 up to c sub k are some constant coefficients. Given that linear recurrence equation, we'll subtract the right side from both sides to make the right side 0. That gives us a sub n minus the sum from I equals 1 to k of c sub I times a sub n minus I equals 0. Now, our next step is going to be to convert this equation into a polynomial equation. How can we do that? Well, all we're going to do is we're going to replace each a sub j with an x to the j. So our recurrence equation turns into x to the n minus the sum from I equals 1 to k of ci times x to the n minus I equals 0. So all we did to get that equation was to replace each a sub j with x to the j. Notice that we can also factor out an x to the n minus k, and this produces a polynomial equation where the left side has degree k. So now we'll solve for the roots of the polynomial of degree k. This gives us k roots, r1, r2, up to r sub k. It's possible that some of the roots might be repeated roots, and that's fine. We will look for an explicit formula of the form a sub n equals the sum from I equals 1 to k of x sub I times r sub I to the n, where x1, x2, up to xk are fixed coefficients. And we're going to have to solve for the x1, x2, up to x sub k. And we'll use the initial values of the sequence to solve for them. And those initial values are a1, a2, up to a sub k. Now, it's not that important for us to use the initial values to solve for x1, x2, up to x sub k. All we have to use are k distinct values of the sequence. However, usually the initial values will give us simpler equations to work with than larger values of the sequence. But it will really depend on the sequence. So what happens if we have some repeated roots? For example, if we have some root r sub I of multiplicity 2. In that case, instead of having an x sub I times r sub I to the n, we replace the x sub I with x sub I plus y sub I times n. In other words, we replace the x sub I with a linear term in n. So the x sub I times r sub I to the n becomes an x sub I plus y sub I times n, that whole quantity times r sub I to the n. We'll see some example with one of those. If you have some root r sub I with multiplicity 3, you replace the x sub I with the quadratic term in n. So a quadratic term in n in general can be written in the form x sub I plus y sub I times n plus z sub I times n squared, where x sub I, y sub I, z sub I are some real numbers that we have to solve for. And more generally, if you have some root r sub I and it has multiplicity m, we replace the x sub I with an m minus 1 degree polynomial term in n. So if it's an m minus 1 degree polynomial term, it means that the number of coefficients that we have to solve for is m. So we have a general form for the explicit formula that we're looking for. That general form on the previous slide, we wrote it right here. It's this a sub n equals the sum I equals 1 to k of xi times ri to the n. That's assuming that all of the roots are distinct, and if there's any repeated roots, we make the replacements as described in this last bullet, and more specifically in the previous two, when we have multiplicity 2 or 3. But those previous two are both encompassed by the last bullet. So our explicit formula is going to be of this form, but we don't know yet what the x1, x2 up to x sub k are. So in order to solve for the x1, x2 up to x sub k, we make a system of equations where the unknowns are x1, x2 up to x sub k, and we build these equations just by using the initial values of our sequence, a1, a2 up to a sub k. And again, I'll mention that it's not important for us to use the k initial values. We just need to use any k distinct values. But we choose the initial values typically because they give us nicer equations, usually, but it will depend on the sequence. And then once we get an explicit formula for the sequence, we're not done yet because we still have to prove that that formula is correct. And we can typically prove that it's correct using induction. So the first example of applying this method, we'll look at how to find an explicit formula for the Fibonacci sequence, and then we'll prove that our formula is correct. So there is our recurrence equation for the Fibonacci sequence. F sub n equals f sub n minus 1 plus f sub n minus 2. We will subtract the right side from both sides. That gives us f sub n minus f sub n minus 1 minus f sub n minus 2 equals 0. We can convert this to the polynomial x squared minus x minus 1 equals 0. So maybe I'll describe a little more what happened there. So first we converted it to x to the n minus x to the n minus 1 minus x to the n minus 2 equals 0. And then we factored out the x to the n minus 2. And that gives us an x squared minus x minus 1 equals 0. And we don't worry about this x to the n minus 2. We just get rid of it. Okay. And we continue. We can use the quadratic formula here because our polynomials are quadratic to solve for the roots, which are 1 plus the square root of 5 over 2 and 1 minus the square root of 5 over 2. You might have seen this 1 plus the square root of 5 over 2 before. It's the golden ratio. So we're going to look for an explicit formula of the form f sub n equals a times 1 plus square root of 5 over 2 to the n plus b times 1 minus the square root of 5 over 2 to the n, where a and b are some real numbers that we have to solve for. In order to solve for the a and b, we just need to use two distinct values in the Fibonacci sequence. So we could use f of 1 and f of 2. Typically, we say f of 1 equals 1, f of 2 equals 1, and then we go from there. The good thing is the Fibonacci sequence can also be defined for negative numbers. So we have this definition, f sub n plus 2 equals f sub n plus 1 plus f sub n. We can use that to write f sub n equals f sub n plus 2 minus f sub n plus 1. And for n equals 0, that gives us f sub 0 equals f sub 2 minus f sub 1, which is 0. So we can use the initial values for f sub 0 and f sub 1 instead of f sub 1 and f sub 2. That gives us a slightly nicer system of equations. And since f sub 0 equals 0, this tells us when we plug in n equals 0, so we plug in n equals 0 up here and here in this bullet. And if we plug in n equals 0 in that bullet, we're taking 1 plus square root of 5 over 2 to the 0th power and 1 minus the square root of 5 over 2 to the 0th power. We get 1 for both of those. Raising something to the 0th power, we get 1. And so we get a times 1 plus b times 1. So f sub 0 equals a times 1 plus b times 1, a plus b, what we see right there, and that has to equal 0. So we see that b is equal to minus a. So b equals minus a there. And our other equation we get from f of 1. So f of 1, we see when we plug in n equals 1 into the equation. So the equation in the bullet right here, we plug in n equals 1 there. We get a times 1 plus the square root of 5 over 2 plus b times 1 minus the square root of 5 over 2 equals 1. And then these two, when we add those together, we can see since b equals minus a, we can substitute that for the b. So we can write a times 1 plus square root of 5 over 2 minus a times 1 minus square root of 5 over 2 equals 1. And the good thing is these parts cancel. So we get a times the square root of 5 over 2 minus a times negative the square root of 5 over 2 equals 1. And that gives us a times the square root of 5 equals 1. So a equals 1 over the square root of 5. And then what does that give us? Well, for our formula, should probably clear that. That's what our formula we get for our formula. So when we throw in the a there, we get 1 over the square root of 5 times 1 plus square root of 5 over 2 to the n. And then our b was minus 1 over the square root of 5. And then that times 1 minus the square root of 5 over 2 to the n. And we can just pull the 1 over the square root of 5 out. And we can write it as the difference of 1 plus the square root of 5 over 2 to the n and 1 minus the square root of 5 over 2 to the n times that 1 over the square root of 5. So that is the formula that we found using the method, but we didn't prove that it is correct yet. So we still have to prove that it's correct. We're going to use induction to prove that it's correct. In order to make our proof a little shorter to write out, we're going to use some symbols for these roots. The golden ratio, the 1 plus the square root of 5 over 2, we write that as phi. We can also observe that the other root, the 1 minus the square root of 5 over 2, that's equal to negative 1 over phi. So we can write our formula as f sub n equals 1 over the square root of 5 times phi to the n minus negative 1 over phi to the n. And we're going to try to prove that this formula is correct using induction. This time, we're going to use strong induction instead of weak induction. We'll have a base case that has two values of the Fibonacci sequence in it. The first value will be f sub 0. F sub 0 we just saw on the previous slide is 0. And that's equal to 1 over the square root of 5 times phi to the 0 minus negative 1 over phi to the 0. Because anything to the 0 is 1, and we get a 1 minus 1, this is 0 in there. f sub 1, that is 1 by definition, and we can check to see that that's equal to 1 over the square root of 5 times phi to the 1 minus negative 1 over phi to the 1. So we can check that right now. We can see phi to the 1, we got a 1 plus the square root of 5 over 2. Negative 1 over phi to the 1, this is 1 minus the square root of 5 over 2. So we're multiplying that times 1 over the square root of 5. And like we saw on the previous slide, it's the same thing we saw. The 1's cancel out. We get 1 over the square root of 5 times square root of 5 over 2 plus square root of 5 over 2. So this gives us 1. So that one worked out. So the inductive step, we have to do that still. We will have this inductive hypothesis where we assume that f sub j is equal to 1 over the square root of 5 times phi to the j minus negative 1 over phi to the j. And this is true for all 0 less than or equal to j less than or equal to k. So that's a strong inductive hypothesis. And we'll use that to prove our next inductive step, which we want to prove that f sub k plus 1 is equal to phi to the k plus 1 minus negative 1 over phi to the k plus 1. We didn't prove that yet. We're about to prove that. In order to prove that, we can use our recurrence equation for the Fibonacci sequence. We'll write f sub k plus 1 equals f sub k plus f sub k minus 1. And then we can use our inductive hypothesis for f sub k and for f sub k minus 1. We write f sub k as 1 over the square root of 5 times phi to the k minus negative 1 over phi to the k. And we write the f sub k minus 1 here as 1 over the square root of 5 times phi to the k minus 1 minus negative 1 over phi to the k minus 1. And how can we simplify it now? Well, what we can do is we have this phi to the k right here, and we have this phi to the k minus 1 right here. We will group them together with this phi to the k that we pull out of both of them. So if we pull a phi to the k out of a phi to the k, it leaves us with a 1 right here. If we pull a phi to the k out of a phi to the k minus 1, it leaves us with a 1 over phi right here. So that's why we got a phi to the k times 1 plus 1 over phi. Now let's look at these negative 1 over phi terms. We got minus, and then a negative 1 over phi to the k, and then over here we got minus, and then a negative 1 over phi to the k minus 1. So we're going to do like we did with the phi to the k's. We're going to pull out a minus 1 over phi to the k term. And we got that minus still right there. So we pull out the minus 1 over phi to the k term. When we pull that out of the minus 1 over phi to the k term, that just leaves us with a 1. When we pull it out of the minus 1 over phi to the k minus 1 term, that leaves us with a minus 1 over phi. And the minus 1 over phi, so minus 1 over phi to the k minus 1 divided by minus 1 over phi to the k, we get 1 over minus 1 over phi and 1 over minus 1 over phi. So we can write that. And that is exactly what we see right here, is the minus phi. So that's why we got a 1 from this minus 1 over phi to the k, and we got the minus phi right there from the minus 1 over phi to the k minus 1. So we can see that both of those expressions are equivalent to each other. And finally, we can simplify this. So the phi to the k times 1 plus 1 over phi right here, I claim that that gives us a phi to the k plus 1. Now, why is that true? Well, the claim is that phi equals 1 plus 1 over phi. Why do we know that's true? Well, we know that phi is a solution to the equation x squared minus x minus 1 equals 0. So phi squared minus phi minus 1 equals 0. So we can say phi squared equals phi plus 1. You can divide both sides by phi, and that's how you get phi equals 1 plus 1 over phi. So the phi to the k times 1 plus 1 over phi gives us the phi to the k plus 1 right here. And the minus 1 over phi to the k times 1 minus phi, the claim is that 1 minus phi equals negative 1 over phi. Why is that? Well, let's take this equation right here. We'll rearrange some stuff. We'll take that 1 over phi, subtract it from both sides. We get minus 1 over phi. We'll subtract the phi from both sides too, so we get 1 minus phi. And that's what we wanted. Negative 1 over phi equals 1 minus phi. So we end up with the negative 1 over phi to the k. So this thing right here, that becomes this thing right here. Negative 1 over phi to the k plus 1, because the 1 minus phi becomes a negative 1 over phi. So that completes the induction. So we just found an explicit formula for the Fibonacci sequence, and we proved that it was correct using strong induction. So let's look at another interesting application of the Fibonacci sequence, which might be somewhat unexpected. So these are a special class of problems that usually called tiling problems, and this one is an especially nice example of a tiling problem. So you can do tiling problems for rectangles of any sizes, and you can use different sizes of tiles. We're just considering a rectangle that's a 2 by n rectangle, and the tiles have size 2 by 1. And the question is, how many ways can we tile the 2 by n rectangle? So maybe I'll draw a little picture of it. So there's our 2 by n rectangle for some n. Here's our tiles. They can be either direction. And we want to tile this with the 2 by 1 tiles. And we want to find the number of ways we can do that. So if we don't know how to do this yet, it makes sense to look at some small values of n and try to find a pattern. So we can look at n equals 1, for example, the 2 by 1 rectangle, and we see the answer for that is obviously 1. Then we can look at the 2 by 2 rectangle. So for this one, the 2 by 2, we can tile this 2 ways. We can tile it like that, or we can tile it like this. So 2 ways to tile that. The 3 by 3, we can look at this one, 3 by 3. So if we do the first column like this, the last 2, we can do them like this, or we can do them like this. And the other possibility for the first column is we do it like this, and that leaves us with 1 column at the end. So these are not really drawn to scale. Let me specify the dimensions a little better there, in case it's confusing. Okay. Hopefully that clears up any issues. So there's 3 possibilities for the 2 by 3 rectangle. And then let's look at the 2 by 4 rectangle. So the 2 by 4, the first column we can do like this. So we can do all the columns like that. The first column, if we do it like that, we can also do something like this. We can also have the first column like that, and then the second and third columns horizontal, and then something like that. And then another possibility, we could have the first 2 columns horizontal and the last 2 vertical, or we could have everything horizontal tiles. So it looks like n equals 4, we got 5. 5 ways to tile it. And for n equals 5, I'll leave that to you to try by hand. We find that there are 8 ways, hopefully. And it appears that we're getting Fibonacci numbers. More specifically, it looks like that there are f sub n plus 1 ways to tile the 2 by n rectangle. So the number of ways is the n plus first Fibonacci number for the 2 by n rectangle. It looks like that at least. And we need to see if we can prove that. So we'll try to use induction to prove this. And in order to do this, we'll define a sequence. We'll call it T sub n, and it will denote the number of ways to tile a 2 by n rectangle with 2 by 1 tiles. So we already found the value of T sub n when n equals 1 and when n equals 2. So when n equals 1, we saw that T sub 1 equals 1, and n equals 2 tells us that T sub 2 equals 2 because there were 2 ways to tile the 2 by n rectangle. So now we'll suppose that n is greater than or equal to 3. And if n is greater than or equal to 3, we have some 2 by n rectangle here. And it goes on maybe. We don't know how long it goes on. There's 2 possibilities for how we tile on the very left of it. On the very left, we can use a vertical tile, or we can use 2 horizontal tiles. So we're going to break into 2 cases. We're going to count our number of tilings by breaking into 2 cases and then adding together the number of tilings for both of those cases. And as long as all of our tilings must fall under exactly one of the cases, then this will give us the exact number of tilings. So case 1 is right here. Case 2 is right here. Now with case 1, we can see if we have a vertical tile on the very left, then the remaining rectangle that we still have to tile, besides that vertical tile on the left, is a 2 by, so 2 is the height, and the length of the remainder is n minus 1. The original was n, and we took out this 2 by 1 rectangle on the left. So we lost 1 from the length of it. Now in this case 2 down here, if we have 2 horizontal tiles on the left, they're each 1 by 2, which means that the remaining rectangle is going to be a 2 by n minus 2 rectangle. Because we had a 2 by n, we removed this 2 by 2 square on the left, which leaves us with a 2 by n minus 2 rectangle. So those are our 2 possible cases. Case 1, we place 1 tile in the first column of the rectangle, a single vertical tile. And that left us with the 2 by n minus 1 rectangle. And any way that we can tile a 2 by n minus 1 rectangle will work for the remainder of that rectangle. So we can see this right here. We have our vertical tile right there. We have our 2 by n minus 1 rectangle. We just tile this. Any valid tiling of a 2 by n minus 1 rectangle can be used for this remainder part. And this part has already been tiled, so we ignore it. So the number of tilings for the 2 by n rectangle that fall under case 1 is just T sub n minus 1, which is the number of tilings of the 2 by n minus 1 rectangle. In other words, the number of tilings of this 2 by n minus 1 remainder, the remainder when we take out this vertical tile on the left. So that was case 1. Case 2 is the other picture I drew, which I'll draw again soon, where we place 2 tiles horizontally in the first column. And I claim for case 2 that the number of tilings of the 2 by n rectangle that fall under case 2 is going to be T sub n minus 2. And why is this? Well, when we take out the 2 tiles on the left, these 2 horizontal tiles, so when we dismiss these, when we forget about them, we're left with a 2 by n minus 2 rectangle. Any valid tiling of this will work to give us a tiling of the 2 by n rectangle. So we can tile the 2 by n minus 2 rectangle with any valid tiling. And that gives us a tiling of the 2 by n rectangle when we combine it with these two tiles on the left. So since there's t sub n minus 2 ways to tile the 2 by n minus 2 rectangle, this gives us t sub n minus 2 tilings that fall under case 2. And we can see that every tiling of the 2 by n rectangle must either have a vertical tile in the first column on the left, or it must have two horizontal tiles on the left. So every possible tiling falls under case 1 or case 2. Moreover, there's no tiling that can fall under both case 1 and case 2, because you can't have both a vertical tile in the leftmost column and two horizontal tiles in the leftmost column, or else it wouldn't be a tiling. So we see that the number of tilings of the 2 by n rectangle is equal to the number of tilings that fall under case 1 plus the number of tilings that fall under case 2. And that's equal to t sub n minus 2 plus t sub n minus 1. So our recurrence equation is t sub n equals t sub n minus 1 plus t sub n minus 2. And this holds for all n greater than or equal to 3. We also saw, again, that t sub 1 equals 1 and t sub 2 equals 2. So t sub 1 equals f sub 2, the second Fibonacci number, and t sub 2 equals f sub 3, the third Fibonacci number. We also can note that t sub n has the same recurrence equation as f sub n. So this tells us immediately that t sub n equals f sub n plus 1 for all n greater than or equal to 1. So we could have also proved this using induction. We could have proved an explicit formula for t sub n using induction. But since it's already clear from the recurrence equation that it's the same as the Fibonacci numbers, we don't have to prove anything by induction. So the explicit formula for t sub n is just the exact same explicit formula as we got for the Fibonacci numbers, except with a plus 1 in the power in the exponent. So let's look at another example of a linear recurrence equation that's a little different from the Fibonacci equation. Suppose that we have this sequence a sub n, and it's defined by a sub 0 equals 0, a sub 1 equals 2, and a sub n plus 2 equals 4, a sub n plus 1 minus 4 times a sub n, for each n greater than or equal to 0. So if we want to apply the method to find an explicit formula for this recurrence relation, we will first subtract the right side from both sides. That gives us a sub n plus 2 minus 4 a sub n plus 1 plus 4 a sub n equals 0. And we can convert this to a polynomial. So we'll get x to the n plus 2 minus 4 x to the n plus 1 plus 4 x to the n equals 0. And we can factor out the x to the n. So we get x squared minus 4x plus 4 equals 0. And we forget about the x to the n. That part doesn't matter. What matters is the x squared minus 4x plus 4 equals 0. And we solve that equation. We find the roots of the polynomial. And we find that we get the root 2 with multiplicity 2. So x squared minus 4x plus 4 is equal to x minus 2 squared. So we're going to look for an explicit formula for our sequence, which is of the form a sub n equals a linear term in n times 2 to the n, 2 being our root, and the linear term in n is because our root had multiplicity 2. So the linear term, we'll write it in the form x plus yn, where x and y are some real numbers that we have to solve for. In order to solve for x and y, we can plug in small values for n, like n equals 0 and n equals 1. So a sub 0, we were told that equals 0, which implies when we plug in n equals 0 into this explicit formula that we're trying to solve for the x and y in, when we plug in n equals 0 there, we get a0 equals x plus y times 0 times 2 to the 0. We can write that as the a sub 0 we were told is 0. So 0 equals x plus y times 0 is just x, and 2 to the 0 is 1, so we just get x. So that gives us the x equals 0 right here. And then we can also plug in 1 for n. So a sub 1 we were told is 2. So the a sub n on the left, we got 2 there. 2 equals x plus, oh, we already know x is 0, so I'll get rid of that. So 2 equals y times n times 2 to the n equals 1. So 2 equals y times 1 times 2 to the 1. 2 to the 1 is 2, so we can cancel these out. So we got 1 over there, so y equals 1. So that's how we got the y equals 1. So the explicit formula we found is a sub n equals n times 2 to the n. But we didn't prove that it's correct yet, so we can use induction to prove that it's correct. And to prove that it's correct using induction, we'll start with a base case. Since we're using strong induction, our base case will include multiple elements of the sequence. So we'll include n equals 0 and n equals 1 in there. We see that a sub 0 equals 0, and that's the same as 0 times 2 to the 0. And a sub 1 equals 2, that's the same as 1 times 2 to the 1. So that's our base case. Our inductive hypothesis, which is a strong inductive hypothesis, is that a sub j equals j times 2 to the j for each j equals 0 up to k. And we're going to try to prove that a sub k plus 1 equals k sub 1 times 2 to the k sub 1. In order to prove that, we can use the recurrence equation. A sub k plus 1 equals 4a sub k minus 4a sub k minus 1. And here we can use our inductive hypothesis. So we substitute a k times 2 to the k for the a sub k, and a k minus 1 times 2 to the k minus 1 for the a sub k minus 1. And so we end up with 4k times 2 to the k minus 4 times k minus 1 times 2 to the k minus 1. And when we simplify that, we do get k plus 1 times 2 to the k plus 1. So that finishes the induction. Here's another recurrence relation problem for you to think about. Suppose that the sequence a sub n is defined by a sub 0 equals 0, a sub 1 equals 5, and a sub n plus 2 equals 10 times a sub n plus 1 minus 25 times a sub n for each n greater than or equal to 0. And the problem is to find and to prove an explicit formula for a sub n that uses no recursion or summations. That brings us to the end of the video. Thanks for watching.